Greetings, everyone. In this paper, I'm going to present choosing how to remember adaptive memory structures for LLM agents. And abstract of this paper is the paper has introduced a framework, memory framework called FluxMem, and it is designed specially for LLM agents that are dealing with long arrays and conversations. Instead of using one single memory structure, it adaptively selects among linear, graph, and hierarchical memory based on the interaction patterns. And the framework also combines this with three-layer memory-based hierarchy. And it also uses BMM-based adaptive fusion for robust memory updates. This leads to stronger response accuracy and consistency on long context benchmarks. So the two key challenges or gaps in this long horizon task spaces, one is that single structure assumption, and the other one is lack of feedback-driven adaptive memory structure selections. So in the single structure assumption, uh, the LLM agent is given one fixed memory structure for all the tasks and conversation types, and basically the example is RAG. This causes suboptimal performance because of long arrays on tasks contain mixed patterns such as temporal progression, relational dependencies, and topic evolution. So single structure can't handle all these things. And coming to the second gap, memory structure is usually fixed in advance and not chosen based on the current interaction. So as you can see in this diagram, there are and there is a query and in the previous systems it only selects it was pre-selected, either we have linear graph or hierarchy. Uh, if we select graph and we give some relational data, time series data, uh, then the LLM agent doesn't perform well. But in this FluxMem, it doesn't have to we doesn't have to pre-select one of these memory structure. Based on the query, the agent selects the memory structure and then answers the query. And structure choice is excluded from optimization, which limits alignment with downstream task quality, response quality, and this also reduces the robustness of distribution. Coming to the memory systems, we have three types. They are flat retrieval-based memory system. This stores facts or summaries in weakly structured store and retrieves them using similarity search. These are efficient but are weak at abstraction or relational reasoning. And we have explicitly structured memory systems. These organize memory as linked nodes or graphs, which this improves relational and temporal reasoning. And we also have policy managed memory systems where we can control what to store and retrieve based on previously engineered or learned policies. But this also have fixed structural biases. And with the memory structures, we have again three types of memory structures. One is linear memory structure, and second is graph, and third is hierarchical. In the linear, this organizes memory in chronological order, and this is best for temporal reasoning and recency-based queries. And we also have graph memory structure. This is in this the information is organized as entities or relations similar to the graph algorithm graph data structure we have, and this is best for relational reasoning and dependency tracking. And finally, we have hierarchical memory structure. This organizes the memory in levels, similar to the we can take as a company. There will be CEO, managers, and then other employees. This also organizes memory in the similar, and this is best when we have something vague query and then we want to funnel down it to some particular query, then this is best for this is best for that type of scenario. And in this paper, they have proposed FluxMem, and it's an adaptive framework, as we said, for the long horizon LLM agent interaction. In this, they organize memory to three layer hierarchy. STIM, MTEM, and LTSM, which we'll look in more detail further. And this dynamically selects among linear graph and hierarchical memory structure, and then uses conversation-aware select to choose the best structure for each interaction, and applies beta mixture model-based adaptive memory fusion instead of fixed thresholds. This is the architecture. And on the left, top left, we have the beta mixture model gate. Uh, and in the on the bottom right, we have how the query will be asked, and the LLM agent selects from one of the memory structure to have that query, and then based on the memory hierarchy and the prompt, it also selects a memory structure, linear or graph or hierarchical, and then based on all this information, it answers the query. The three-layer memory hierarchy is the first one is short-term interaction memory. This is the cache type memory where the most recent where the LLM agent buffers the most recent pages for a faster access, and this is useful when the agent needs recent context, such as answering a follow-up question from the last few runs. And we have midterm episodic memory. This stores episodic memory units where each unit contains multiple semantically or temporally related pages. So all the memory will be divided into episodes, and then it will be uh, the current query will be sent to each one of the episodes. And this is useful for recalling specific past events or episodes from a longer interaction history. And we have long-term semantic memory. Uh, Here, that once the query is asked, it has to forget some of the things and has to store some of the things. So if we think something that is important, it needs to be stored in this long-term semantic memory. And so we maintain a consolidated durable knowledge abstracts from the past interactions. This is useful for retrieving stable user facts such as their name, address, or other details like that are persistent across all the sessions. Then we have multi-structure memory organization, as we have discussed previously. We have linear memory, graph memory, and hierarchical memory. And these are used in various scenarios. And these structures are used for different retrieval behavior over the same interaction history, which is why one structure is not enough. And this is how we will store the information. First one, we have conversation history, where we store all the user agent interaction pages with respect to time. And each P1, P2, P3 have a user and an action for that particular instance. And then we have the query, which is QTs, which is current query. And we need to generate a response by T based on the current query and retrieved memory from the conversation history, and also by selecting a memory structure that is useful in this case. And then we have conversation-aware structure selection. So Flux memory treats memory structure selection as explicit learnable decision. And we have a conversation-aware selector which chooses the best structure for the current interaction. This is selected based on several features such as entity density, topic diversity or topic transition, and question and answer pattern, and time span, and temporal density. This allows the system to adapt structure choice instead of using one fixed organization for all the cases. So, the selector predicts a memory structure from the conversation features while trying. So here the offline training means we just we have a previously prepared data set that will be used to see whether we are getting a good response based on this reward structure where we take two. RJT is the response quality reward and RMT is the memory utilization reward. And we have this RTS, which is the combined reward, and we take argmax of it for the offline target structure, and then use this and we use different memory structures to see which one is giving the maximum reward. And then based on this learned parameter, we select the memory structure while performing the real-time query solution query while giving the query to the agent. And finally, we have BMM-based memory fusion, where prior method often uses fixed. Previously, we used fixed similarity threshold to decide whether two memory units should be merged or not. This is specifically used for the episodic memory, where we have so many pages and we have to decide uh, the current page should go to into which memory, and they use a normalized similarity score, and they divide that into two, where they based on that X, they divide that into rejection or accept. And based on this too, we have a BMM gate or threshold that can be used uh, to to send that particular page into the memory system. This makes the fusion more robust under noise and distribution shifts. Instead of previously we have only threshold, and if we have some noise or something that used to go over the threshold, and we don't uh, have the cushion to see whether this goes into the correct episode or not. And for in this paper, they used two data sets. One is Persona Mem and another one is Locomo. Persona Mem evaluates whether the agent can remember and use personal preferences and use specific information access over across long interaction. This is used to test the personalized long-term memory behavior and is evaluated with accuracy. So in this, there are no conversation repetition. It's just mostly question and answer. And in Locomo, it's more of conversational memory instead of question answer type, like unlike the Persona mem. So these two test on different abilities of the Flux mem. And in the Locomo, the evaluation metrics are F1, Blue1, and Rogel. And uh, these are the metrics that are used for uh, these are the experimental settings that are used. And coming to the results, the both the FluxMem performed well on both the data sets. It has an improvement of 9.18% on 18% on PersonaMem and significant increase in each evaluation metrics in the Locomo. And FluxMem is more stable across diverse interaction patterns than fixed structured baselines. And in this, they have also done ablation studies where they have removed each section, like they have put fixed structure, and they have did They have basically tuned several parameters and saw how that affects the performance. And these are the graphs that are see. And coming to the conclusion, existing memory systems rely on a single fixed structure, which is not sufficient for the long conversation. So we introduced FluxMem, which adaptively selects linear graph and hierarchical memory structures, and a conversational-based selector chooses the best structure for each interaction. And PMM-based memory fusion makes the memory updates more robust than fixed threshold merging, and this leads to the strong results on personal and Locomo. That's it. Thank you for giving me this opportunity.